So thank you, Mr. Chairman, and I may say thank you, dear friend. I should say dear old friend, not because he's old, but our friendship is old, maybe you know. So let me express my gratitude to the organizing committee of this colloquium for inviting me to deliver this opening lecture. As an old-timer, and time-wearer also, this brings back to I have to get accustomed to this. Oh, it works. It is, yes. It brings me back 50 years ago in Moscow in 1773. So at the time, Professor Jean Leroux Kerizel, we know him as Jean Kerizel, was the president of our National Society, and he was given the opportunity of celebrating the bicentenary of Coulomb's paper. So today, as already said, we are celebrating the 250th anniversary of the presentation of Coulomb's memoir, Coulomb's essay, to the Academy of Sciences. It is, as already said, it is considered a popular landmark, especially in soil mechanics, although it treats with stability of volts, but for us, and our topic today, topic of interest, is soil mechanics. A few words about the presentation. The presentation was made by Bossu. Bossu was an abbot. He was a member of the Academy, and he had been Coulomb's former teacher in mathematics. The presentation took place in 1773, exactly 1 year after Coulomb returned from Martinique, an island I cherished, from Martinique, where I had been working during 8 years, building Fort, now known as Fort de Sey, which was for Bourbon, sorry about it. And so he was in charge of all practical works. This is how Fort Bourbon was in 1776, I would say. And Coulomb says that the memoir was written at the time as a practical, theoretical issue of the works, the practical works he had been in charge of in Martinique. One point is important here is that the word utility, Coulomb wanted his memoir to be useful to what the people only called the artists. The title of the essay, we have already seen, is interesting. We have to retain the word statics and the words rules of maxima and minima, because they describe exactly the rationale that will be developed in the memoir. Let us start with the scientific contemporaneity of the memoir, of Coulomb's memoir. It came after Galileo, the Discorsi, 1638, the Discorsi where you find the famous problem of the cantilever beam, often considered as the origin of field design rationale, but a very faint origin, I must say. Also, it comes after the elasticity Hooke's law had been revealed in 1688, as far as 1678, sorry. And here you have the work by Coulomb. Coulomb never refers to Galileo, despite the fact that he himself studies the same problem in the essay, as you will see. But perhaps it was common knowledge. It was not just usual at the time to refer to somebody. But what is more important is to see that the analysis by Coulomb comes before all these people. Lagrange, 1788, the principle of virtual velocities and the introduction of resisting forces. Cauchy, 1823, introduction of the stress vector, stress tensors that are the basis of continuum mechanics. And finally, Tresca from 1864 to 1870, a lot of memoirs to the Academy of Sciences, which are considered as the origin of the theory of plasticity. This is what Coiter wrote. So if we want to comment Coulomb's work, we should not take into account works that came after him. We have to comment it in its own temporality. Now let us start with Let us start with the memoir itself. The first and the cornerstone of the memoir is the problem is friction and cohesion, or more exactly, the definition of what the Coulomb considers as resisting forces, which he calls coercive forces. He insists on the fact that they are not active forces, but those forces are only assessed through their limits of resistance. In other words, you don't know those forces, you know that they must stay between two limits. We will see exactly what it is in the present case. Also, we notice that he listed the resisting forces as friction and cohesion. So as far as friction is concerned, Coulomb refers to Amonton. Amonton was a French scholar, although people usually pronounce it as Amontons, but he was French. He was born in Paris. So. And this Amonton gave this statement: the resistance to friction is proportional to the pressure exerted. The coefficient of friction was 1 over n, which will be I will change it to tangent phi in all the following. It maybe sounds strange that Coulomb refers to Amonton, since it has already been referred to as somebody who has worked on friction himself. But we must remember the temporality. Coulomb's own researches on friction would be presented 8 years later to the Academy, 1781, and he will win a prize of the Academy for his researches. So he refers to Amonton and uses the law, frictional law, which is proportionality. Friction and cohesion. For cohesion, he refers to van Musschenbroek. But strangely enough, this is a bit mixed. I'm sorry about it. It shouldn't show that way. He was a corresponding member of the Academy of Sciences. And Essay, this was written in the English at the time, which was Latin. And cohesion is measured by the resistance that solid bodies oppose to the direct disunity of their parts. Total cohesion is proportional to the fracture surface. This reminds us of Galileo's statement in the Discorsi, where Galileo speaks about a certain cement which held the parts glued together, and so on and so on. So the same ideas come. And finally, for Coulomb, as he said, he had two components. Those two components, cohesion and friction, are additive, independent additive to material resistance. Van Musschenbroek and Amonton. Now it's the core of the memoir as regards its legacy to soil mechanics. It comes from the Coulomb's analysis of the stability of a retaining wall. This is obviously the works he had to work on when he was working in Martinique, and retaining walls for a fort are very useful, of course. In fact, he is looking for the maximum pressure exerted by the soil bulk on a retaining wall. This is the drawing you find in the paper. And to study this, he uses a thought experiment, what is called now a thought experiment. In fact, he delimits a solid triangle, solid meaning that it is considered as a solid body. A solid triangle is delimited in the bulk of soil. It is subjected to gravity. It is sustained by a force, horizontal force, A, and it is retained by resistance of soil along BA. So it's you want to study the equilibrium of this solid triangle. So the problem is, how can we assess the value of force A, the horizontal force here, without causing the triangle to move? Force A must be such that the triangle doesn't move either upward or downward. This is a problem. So equilibrium, with the fact that we have to deal with resistance, not a given forces, not an active forces, but a coercive force. So If we study, I said that this force has to stay between two limits, upward limit, downward limit. So Coulomb will consider two cases. The first case, he says, well, force A must prevent CBA from flowing downwards. So we are looking for the minimum value for this force A to prevent CBA from flowing downwards. This will be attained when the resisting force along AB will be directed upwards, because it will help, and of course when it will be fully mobilized. So we have to study equilibrium and resistance. This has to be compatible, and the minimum value of A will be obtained when resisting force is fully mobilized upwards along BA. This gives us a value which depends on the triangle, which depends on alpha, and this is the value of this force with changing, for instance, phi, tangent phi. I said we will find it as 1 over n and so. So A must be at least equal to A of alpha. Then also, force A shall not cause the solid triangle to move upwards. So imagine the force is made to increase and tend to impulse the triangle upwards along BA. So we have to find the value, the maximum value of force A that will not cause the triangle to move upwards. So the reasoning is the same as before, but for the fact that in that case we will assume resisting force along BA to be directed downwards because it will help, it will oppose the motion, upward motion, and of course also we will assume it to be fully mobilized downwards along AB. So we have a value which is this time a maximum value for A to be not to cause the triangle to move upwards. So A should be inferior to A prime of alpha. And then we come to a conclusion. He comes to a conclusion and says, well, it has just been proven that when cohesion and friction both contribute to maintaining the triangle at rest, the limits to the value of a force that can be exerted at point F without causing triangle to move will lie between A of alpha and A prime of alpha. But this conclusion should be valid for any triangle, which he has chosen this triangle depending on alpha, but it should be valid for any triangle depending on the parameter alpha. So this brings us to the title. It depends on alpha, rules of maxima and minima. We will, let me go back, if I can. Here it is. A of alpha, we should look for A of alpha, which is the maximum pressure. We should look for maximum of A. It is, I would say, the lower bound. We should look for the maximum value. And A prime of alpha, it is the upper bound. We should look for its minimum value. This is what Coulomb says. The limits of the horizontal force that can be exerted, and so, will lie between the limits where A will be a maximum and A prime a minimum. Then, of course, he uses the rules of maxima and minima, which is only using the derivative, and he obtains the result. But what I will insist on at that point is that, to my personal knowledge, it is the first case, the first appearance of the concept of estimates as a solution to a problem. Usually, a solution is something equals something. Then the answer is it must stay between limits, and we will look at these limits. I'm sorry for the way the slides appear. It's always a problem of compatibility. We tried everything with Alain. It should have worked, but it doesn't. Sorry about it. So, of course, maximizing A of platform, Coulomb did it, this is active thrust, but it is still a lower estimate. Why? Because Coulomb is aware that he should have considered not only triangular wedges, but non-triangular wedges, and he explains it. Well, I've assumed, he says, I've assumed that there were triangular wedges. This was only with the desire to be useful, remember, utility, to be useful and accessible to the artist. The artist, not the artists as we understand them now, but the artists that were, as they were called at the time, people you use reasoning on their hands to work. You see, those are the artists at the time. But if we would want to determine the curve that produces the maximum pressure in an exact way, here is, I think, the way it could be done. And it sketches out a method. Well, obviously, it falls upon the problem, which is determining the resisting force along curve BG. So it gives a kind of hint. It is a slice method. I would call it a slice method. And for the problem, it will concentrate here. And for this, it will consider the little wedges and treat them as a big wedge. Doesn't go further. We will not go further either. It didn't consider passive thrust, but you will know that we minimize with respect to alpha, and we obtain an upper bound estimate of the resistance opposed by solid mass to upward impulse, that is passive thrust. So we have active thrust and passive thrust, but it did not give the names poussé and buté in the essays. They don't appear. So now let us go beyond Coulomb's analysis. Well, I wish we retain some governing principles. First, clear distinction between imposed loads and resistances. Second governing principle, the necessary condition for stability is that equilibrium of the structure must be mathematically compatible with the resistance of the constituent materials. Second principle. Third principle, we will express this necessary condition, often in a weaker form. We will derive constraints on the imposed loads and the loads exerted on the structure as necessary conditions for the stability of the structure. And then for principle, we use optimization processes to tighten the constraints we have obtained, as Coulomb did. These are the four principles I would retain. But we have noticed that no energy concept has been ever involved in this. And of course, energy was not, I should say, popular at the time. Not yet. So if we try to look following Coulomb's track, and of course this is not exhaustive, it doesn't tend to be exhaustive. We can list Fellenius slip circle method, Rendulich's log spiral method, Taylor's 5-circle method, slice methods, and so on. And as I wrote here, those methods often call for complementary assumptions about resisting forces to make the problem statically determinate. You have no complementary assumption, of course, the Fellenius slip circle when phi equals 0, no complementary assumption with Rendulich's log spiral method, because it is not for this, it is done exactly for this, but you have complementary assumptions for other methods. Well, we may have another idea, since we are after Coulomb, we know something about motion, about some principles and so on. We'll try some kind of kinematical or energy balance viewpoint. The idea is we know that checking a global equilibrium is equivalent to writing that the work by driving forces can be balanced by the work by resisting forces. So we can have this idea and try to write this down. And by the way, this would give us a way of analyzing the stability of structure. The problem comes that the work by resisting forces under the constraint imposed on material limit of resistance is often not determined. You need you need complementary assumptions which happen to be exactly the same as in the preceding slide. As my assessor, when I was doing my thesis, said, if you don't eat it crude, you eat it cooked, but you have to eat it the same. So how can we get rid of this problem? Can we overcome? Well, I suggest that we overcome with the theory of field design. The theory of design comes straight and stems solely from the governing principles and exactly from the two first paragraphs of the governing principles that are here. From these two paragraphs, you can define what we call a domain of potential stability. Domain of potential stability, which means that any imposed loads that satisfy the compatibility between stability, between equilibrium and resistance, is a load for potential resistance. I explain it here. Let us assume we have loads that depend on parameters, loading parameters, for instance, 2 parameters here. And in this space, all those loads for which equilibrium and resistance are mathematically compatible, they form a set where stability is only potential, because what we know is that outside K, instability is certain. It is only a necessary condition, but outside K, instability is certain. Let us see let us revisit Coulomb's analysis, for instance. Gamma A, here we have, for a given value of gamma, we have active thrust, passive thrust, and on both sides, equilibrium and resistance are incompatible. And what we did with Coulomb, what Coulomb did for us, is that we obtained a lower bound estimate of the maximum pressure on the left-hand side, and he didn't do it, but we did it for him. We obtained an upper bound estimate of passive thrust. And this may be called a statical exterior approach, but what you understand is that such an approach is rather tricky. You have to be always cautious, because we are working with maximum, then minimum of the maximum, or the maximum of the minimum, and sometimes people get mixed with that. So it would be interesting to find another way of delimiting the domain K we have just seen. And so for this, we look for a magic tool. The magic tool was provided by Lagrange in the form of the principle we call now principle of virtual work, but at the time was the principle of virtual velocities, which personally I consider a better terminology, but that's not important. Mixing the two first paragraphs and the principle of virtual work provides a method, convenient method, easy to handle, of determining that equilibrium and resistance are mathematically incompatible. It gives us a method which is simple, a kinematical exterior approach, but I should see in your eyes that you find a contradiction with what I said before. I said we had a problem with the work by resisting forces. So, where is the magic tool? What does it give? The magic tool is here in the word maximum. The maximum resisting work can be determined without any complementary assumption once you know the strength criterion of the material. Unambiguously mathematically defined does not call for any complementary assumptions. So, once you have the strength criterion, mathematically you have the maximum resisting work. It is one or the other, those functions are linked to each other. This is what I said. And by the way, it happens that it is obtained through a normality rule. This normality rule, I insist on this point, it is purely mathematical. It has nothing to do with I would say, the word, I'm missing the word. It will come afterwards, sorry. Age passing. Okay. So this normality rule makes it possible. Constitutive equation, that was the word. Nothing to do with a constitutive equation. So this maximum resisting work is obtained mathematically from the strength criterion. It is either finite or infinite. It depends on the collapse mechanism, the potential collapse mechanism you are considering. It is potential. And then, with this, you have a method, which I designed here, which makes it possible, with this simple statement, which is possible to delimitate K from outside. It is an exterior approach, a kinematical exterior approach. So we have two approaches, one which is obvious, but not very convenient, not easy, not useful, I would say, and the other one which is very practical, which is once you have derived your maximum resisting work. In fact, it is the most often used method. For instance, even when people are not aware of it, for instance, the method of characteristics, which may seem to be a statical method, in fact has been proved so many years ago that it is most often a kinematical method within this framework. So let me conclude. Before the conclusion, this is last but one paragraph. Well, yield design or limit analysis? What is the difference? The difference, I would say here, is plastic, but you will see, not so important. Let us sum up. For instance, yes, this is mathematical theory of plasticity. All those names, you know them, even if you can't read them completely. It is Saint-Venant, of course. And up to Hill in 1950. In soil mechanics, famous names are Drucker, Prager, Hill also. Okay. So we have just seen what the theory of yield design was. It starts from strength criterion. From the strength criterion, as a data, only data, you define the notion of a potential stability, statical interior approach, which is the interior of K, and using the notion of maximum resisting work, which is a mathematical result of convex analysis, a mathematical normality rule, you can have those two methods, but what is important is the kinematical exterior approach we have just seen. Now, what about plasticity? Well, two data in this case, plastic yield criterion and plastic flow rule as a constitutive equation. You have to, know those two. And if you use the theory of a plastic potential by von Mises, then those two are linked to each other, and the constitutive equation is a normality rule. It is the same exactly if you substitute the principle, the preceding plastic potential by the principle of maximum plastic work by Hill, the same. So in this case, the normality rule is the constitutive equation. And what are the results? The results are you have an existence theorem, and you should not see anything below. It's an existence theorem which states that assuming all this, there always exists a solution to any quasi-static elastoplastic process. If the material is non-hardening, then the existence theorem is only valid within a given domain, which is delimited by limit loads. This is only for non-hardening materials, and then this domain can be also you have to delimit this domain, you have upper bound theorem and lower bound theorem. This is what happens with all the bulk of mathematical theory of plasticity. You have all this. The important point is limit loads, is existence theorem, limit loads. But if you want to, the problem is, what about this normality rule? Even assuming soils to be plastic, is the normality rule valid for the soil? It is questionable. So let us try to make a comparison between those two theories. On the one side, mathematical theory of plasticity. On this side, the theory of field design. The difference lies in this line. This line. On the one side, you have an existence theorem, which means that for all loads up in the lower bound theorem, which is up the slide, you have a solution to the problem. On this side, you say that you only have potential stability, and so that means that for the loads that are up, only potential stability. But below, the results are the same. In plastic limit analysis, for loads that are up, that are superior to limit loads, there is no solution in the theory of field design. For loads that are superior to extreme loads, instability is certain. In other words, it is exactly the same. In other words, it means that the results of the upper bound theorem in plastic limit analysis do not depend on the fact that normality be a plastic constitutive law. They are valid even if it is not a constitutive law, because this proves they are valid. So this is what we shall retain. This part, the grayish part here, is the domain of relevance of the theory of field design. It does not call for the validity of the normality rule as a constitutive equation. And in fact, it proves that limit analysis does not depend on normality rule as far as you look at the loads that are the limit loads or up superior to the limit loads. Difference, which is only the existence theorem. So yield design or plastic limit or limit analysis, the same. I used yield design because I wanted to try to find a translation to the French calcul à la rupture, but this is not really important. Now it's time for my conclusion. I think I'm still in time. First, as a conclusion, we must retain what I call the governing principles. I think the first paragraph is very important, especially when we are dealing with reinforced soils. Dealing with reinforced soils, we look at the kind of reinforcement. Is it active or passive? This is the difference between resistance or active force. The difference, imposed loads or resistance, active or passive. This is very important. Then all this has been already seen. Second point I wish to retain is a kind of caveat. Whatever its sophistication, which may lead to remarkable theoretical results, and we love remarkable theoretical results, whatever the discipline concerned, not only in soil mechanics, other people also should say, any mathematical model is only valid insofar as its underlying hypotheses are verified. And with this, I thank you for your kind attention.